So if you look around, what we built, right, be any roads, bridges, utilities, or cities, depend on how well, okay, you understand the surrounding world, the physical surrounding world around you. So in this session, we will look at some of the modern tools that allow us to capture the world with sub-centimeter accuracy. Then analyze it digitally and produce even digital twins for infrastructures. And then at the end of this lecture, I want you to see that 3D geospatial data is not just a mapping tools, but as a decision-making foundation for engineers. The next one. So why is geospatial matters? To think about a project or whatever that you have studied, the first question you ask is, where exactly is the place and what is on that place? What is the terrain like? So geospatial context data will give us that context. It will tell us the elevations, the physical ground features, vegetation slopes, and built-up areas where a designer, engineers can design the future structure that he wants. So in the past, okay, we rely on 2D ground survey that will take days or weeks. But with the new modern technology, this will cut down the duration to probably a couple of days. These revolutions in data correction means that the design can be faster, reduce rework, and make safer data-driven decisions. So let's take a look at how far mapping has come. We have started off with a 2D survey, basically using total station GPS data to produce terrain contour. But it only gives some basic information, but not the real shape of the environment. So we move on to 3D. 3D through LiDAR photogrammetry will give us a very dense information point cloud that truly represent the terrain. And later on, we'll go on from 3D and to digital twins. So digital twins is where geospatial models are linked with real-time data from sensor, making them a living model of an infrastructure. So, no. Okay, so if you look at this is what we have for 2D topographic survey plan, where informations are a bit sparse and it's flat, typically flat, but you have some cross sections that you can touch through the terrain to show engineers how the terrain is. But the whole thing is that you can only give at a certain interval, and you do not see the whole terrain of the shape. So if you go into 3D, we will have able to generate DTM, and physically you can see how the shape looks like.
So actually, this is one of our sites. It's actually behind Furama Riverfront Hotel. And this is the slope failure that if you go on Mothership and you type in, you can see the slope failure in 2021. Actually, Mr. Hing went there to do like both a 2D topographical plan and a 3D digital terrain model. So this is actually a live site.
So by tagging on to point clouds onto this DTM, you were able to see much the next slide. You were able to see a much clearer details of what is actually on site, where you have the whole feature, including the trees, the slope failures, where it fails, and what sort of information that has been on the slope has been captured all the ways, right? Okay, next one. The other technology that you can look into is by flying UAV, which is a good way of capturing places where access impossible. So using a UAV, you can look from the whole area from the sky and see the ground, what is on. So this is one of these construction site that we need to know the progress of the construction work.
So you can see with the UAV, actually, once you get your clearances from CAS, when it goes to a very high elevation, you can see the far view of the site, and you can start to see the shafts of the construction, how they carry out the construction and the progress of work. So it's another way of capturing like aerial photograph or aerial point in time on the site situation and site progress.
No. Okay, we talk about digital twins, and I think this is a very new term to everyone. The imagination is that we always thought that it's a photograph as against what the geospatial data. However, if you look at digital twins, what it means is that you are putting sensor onto the structure and you model the whole thing into the geospatial data. And every live movement detected by the sensor will be fed back onto the control rooms where decision making can be done. Okay, the technology we are using depends on the skill and the precision that we need. So we have a few type of technology. The traditional survey, which is the total station and GPS. I think I presume your earlier class have taught you, the lecturer have teach you how to use the total station and probably the GPS. However, the disadvantage is that the collection of data is very sparse. So it's actually good in term, if you use total station and GPS, it's actually meant for collection of control points where it's you need a lot of accuracy. And for the other one, UAV and LiDAR, the cloud corrections, the data collection is very dense. However, the disadvantage that we have here is we have a lot of heavy processing. So you need a very powerful computer to process all the data that you have been collecting. The next one is the digital engineering era, which is currently we are moving towards that direction, where you have BIM, GIS, and sensor. to create, excuse me, create a live 3D model. But the cons is that the integration is very complex. So you need a lot of engineering factors. We need electrical engineers, mechanical engineers, civil engineers, and probably architects, everybody to be involved.
So I'm not sure how many of you actually have worked with 3D mapping softwares. Actually, when they scan, you have like millions of data points. So most of it you don't actually use. You have to sort of like erase it and take time to take away the noise and take away the, and actually what Mr. is trying to say is that it's fast to capture the information. At a snapshot, you can take a lot of information at one go, but you end up spending hours in front of the computer trying to clean up and post-process the image so that we can use it for computation later on.
Okay. So for the next probably 1 hour or so, we will cover topics like fundamentals of 3D geospatial and the coordinate system, the acquisition, and we'll look at the processing, modeling, and probably some of the applications that survey engineers will be involved. And we also look at the future trend and what is coming up for the future. Let's go to the next one.
Fundamentals.
Okay, we start off with the basic. We will ask ourselves, what is geospatial data? So geospatial data are points of data that you collect to describe where something is on the earth. So traditionally, we are looking at 2D, which is X and Y. And these points have 2 components. We have a spatial components to tell you where are these things, and then we have the attribute, which is tagged to it, that what are they. So to have a 3D geospatial data, you will add in the Z value. So Z is the elevation, where you will combine everything and you have a sort of representation of a 3D space in space, a point in space. So this 3D dimension actually is very crucial to civil engineers, because many of the problems that are faced by civil engineers in the determining of slope, cut and fill, drainage, all this depends on the Z value. So Z values play a very critical part in the studies of for engineers. So for spatial data, we typically put it in 2 different factors. We have raster, and then we have the vectors. Rasters are more like imaging, photography, where you are looking at grids of pixels and cells to form an object. And for vectors, vectors are points, lines, and polygons, where you will draw, most likely you use it in your CAD software. Those are the vectors data. This is the examples of, if you look at the left-hand side of the screen, it's just a simple vector image. And on the right, you will see aerial photography taken above the campus. And this in raster image, we call it raster image. So raster image, if I were to zoom it up to much closer, what we mean raster image, you have rows and columns pixels forming having attributes of the Z, and reflectance value on this to form an image as just like a photograph. If you look at it. So with all the raster vectors, we need to group them up and to put it into a sort of a geographical system, a coordinate system where you can particularly know that where are your location, where is the position in terms with reference to the world, right? So we have two types: the geographical projection, and you have the projected plane projection. So geographical means it's the long and left grid. Project is the UTM, the universal transverse Mercator system. And with these two types of coordinate system, we do still have the datum that is tagged to this system. So in geographical long and lat, we usually goes with WGS 84, which is we call it the World Geographical System 1984. And in Singapore, we are using the SVY 21 data. So if you look at what we trying to present is what I'm going to present is when you look at the whole Earth, this is the geographical map, right? So it's in a sphere. To get into projected coordinate system, you will have to cut the whole sphere and spread it out, and look at it as a piece of paper in the horizontal plane. So this is what we meant by geographical and plane. Right. So this is we. Okay, let's look at how from the 3D conventional survey we move forward to 3D point cloud data. Okay. So point cloud survey consists of millions of XYZ points measured by LiDAR or by photogrammetry. So each point will carry information of intensity and colors. Right. So how do we capture all this? We were using terrestrial LiDAR, or we use aerial LiDAR and UAV photogrammetry to capture all these dense point clouds. And the output format is generic file of E57 plus XYZ and or PTS. So to how do we convert after capturing all these point clouds? We need to convert it to the certain formats where it's readable, easily presented so that engineers can do their design on. Then we convert all these points using certain software and to create thin. We call it triangulated irregular networks. And from there, you were able to produce certain digital elevation model or digital surface models. And these are good in the applications such as volume calculation, cross-section analysis, and slope or contour generation. So if you look at what is thin, thins are a lot of triangles from the XYZ point that has been captured. So every point we have certain values. So they will start to join each and every one together to form some triangles. That's why we call it the word triangulated network. And if you were to click a certain point between this line, there will be information calculated on that line.
So I think the basis of most of the 3D models and especially the digital elevation map is based off this concept of the triangulated irregular network. And actually each and every point is linked together by a line. And the difference between the points, actually, they are all similar to your survey. They are all sort of like interpolated. So then you can get like a very dense network of additional data points to produce like a high resolution map later on.
But just a careful reminder is that the smoother this triangle is, when it is more smooth and cleaner, it's good for it. But then don't over smooth it, that it will remove the real world condition. So for instance, if you smoothed it to too smooth, then you will not see any hill or this valley, right? It becomes a flat, almost a flat surface. So try not to smooth it until to an extent, right? So we have the four different type of or three different type of method of capturing, and the accuracies of all these capturing such, they have their own accuracy, and then it all depends on what type of application that you are going for, and so that you can do a decision on how you're going to do it and which type of system you are going to apply. So if you look at GPS and GNSS, they are very sparse. So normally you only use for control points and some survey points. Then if you need something that is very dense, you will go for LiDAR, terrestrial radar. And for general site preparation work, you can proceed with photogrammetry or UAV. So let's look at the overview of this modern mapping technology. We have satellite-based remote sensing, UAV, drone photogrammetry, and then we have LiDAR. And LiDAR, we have few applications that we can hook this LiDAR onto. For instance, you can put it on the UAV, you can put it on top of a car, or you can use a handheld backpack and to capture all these point clouds. So to compare the technology is satellite and UAV, they will use a sort of sensor, a passive sensor, to capture the images. While LiDAR is using an active sensor technology. So what is a passive platform? So passive means we use natural ambient energy, such as sunlight, right, to capture the surrounding. And active sensor means they will emit their own energy, a pulse energy, and detect the reflected energy back to where the sensor is. Right? So if you look at both scale, they have their advantage and disadvantage. For satellite, you can cover one goal, you can cover kilometers of square meters. And for UAV, if you want high resolution, more details application, then LiDAR is the one that you need to go. So there's certain advantages and disadvantages, and also we have cost and flexibility that involved in this. So if you look at a sort of satellite imaging, so satellite imaging they are able to penetrate through vegetation, clouds to create bare earth DGM. But of course, it's not using the passive. They need to use the active sensor, right? And for UAV, we are very flexible. So UAV can be anywhere that you can use, right? Without any restriction. Of course, in Singapore, of course, there are permits that you need to apply before you can operate. So if you see satellite-based mapping, we talk about satellite. So we have sort of remote sensing using passive optical imaging, and then we also use active, which is using radar, right? So some of the provider, international provider, we have Maxtor, we have Planets and Airbus that if you look into your Google Earth, you probably notice that Airbus is the provider. So the output will be DTM autophotos, right? So, however, the resolution is very far apart. It's in terms of meters rather than millimeters. So these are it's good for satellite based. It's good for large scale planning, especially like flood analysis, then terrain modeling. So if you look at differences between opticals and radars, satellite radar, opticals sensing, they use this passive system that you base on sunlight to create imaging. It's just like your photograph, your camera. So your camera depends on lights to capture the images. So it's actually it's a passive system, right? So the whole thing is actually restricted by time of the day and by the atmospheric cloud. So radar will be a better solution if you want to capture more details. So they are using microwave pulse, which allow images to be captured irrelevant of atmospheric condition and or even vegetations. So radar can really penetrate right through onto the ground. So some of the high intensity radar were able even to shoot all the way down to the soft ground until they hit the hard ground, hard layer of the earth. Right. So looking at this satellite imaging, so if you are using optical image, if you look at the dark side, those are obstructed by the clouds. So your signal, the signal will not be reflected back to the satellite to capture the image. Well, if you are using a radar, a pulse, a microwave pulse, this microwave pulse will penetrate through the cloud and with the vegetation and all the way down to the ground. So it will reflect back and the satellite sensor will capture all the details. So a better picture for you all to understand passive and active. So he put some much clearer one. Hopefully you all can understand all this, right? If we use UAV drone photogrammetry, we are using that for 3D reconstruction, right? So in terms of UAV and drone, practically the typical workflows are you need to do a very proper flight plan. Where you want to fly, how high you want to fly, and what is the overlap. So overlapping of photographs for to collect 3D data, you need to have an overlap of 30%, minimum of 30%. Anything that is less, your whatever information that you collect will be useless, right? So just take note, you need an overlap of a photograph to have 30% overlapping. So coming back is that, so your planning work you need to plan in such a way when you fly and when you want to capture, where is this 30% is, right? And of course, you need to have a proper planning to plan where is your ground control point. So this ground control point will at the end teach and push whatever photogrammetry that you have captured into one whole scene. So what I'm saying is that the overlapping of the 30% means you can take a flight from end to end, and then when you make a return flight, this gap of coverage between this part and this part, you need to have a 30% overlap so that you can have the details around here. So if you don't, if you fly, and then your flight planning is maybe further up, then there's no coverage in between, right? So we have the advantage of using UAV is that if it's fast, flexi, the cost is a bit lesser, and of course you still have that dense 3D data, and since it's image, it's easily visualized. But the disadvantage will be it's weather dependent. If you have raining weather, then you can fly. Even if you have a slight strong wind, that is also an issue, right? So you also have the authorities to take care of, where you need to apply all the permits. And of course, the accuracy, as I say, it all depends on how well your ground control point is established. So we look at LiDAR. What is LiDAR? So LiDAR stands for light detection and ranging. So how this LiDAR able to tell you your X and Y, right? So the measurement is actually they are pushing a sort of laser pulses in every second from the sensor, and they will collect back what is been reflected from the object back into the sensor, and they will use the formulas of the distance, which I will later, they will, when you're applying this distance, the formula, the distance, the speed of light will multiply by the times of elapsed and divide by 2. Why you divide by 2 is because you go first time, you will hit the object. Then from the object, it will reflect it. So you need to divide by 2, right? So this will determine the distance, the length from the LiDAR equipment to the object that you want to measure. So the simple diagram will show you how LiDAR sensor works, transmitting, right, the LiDAR signal, reflect onto object and comes back, and it keeps collecting back into the sensor, and they will calculate the distance. So with the distance and with your sensor, your LiDAR sensor, which is having coordinates, has been coordinated. That means you have a sort of XYZ information that is been key into the sensor. So with that, you're able to do a sort of calculation to determine what is the position of this vehicle, right, in terms of XYZ. So if you look at that's on what I said, combining the range and the obsolete position of the sensor, and whatever you even include IMU if you need the orientation, right? You were able to achieve a precise XYZ coordinates then of the point in that environment. So okay, some pictures of the LiDAR systems that is has been around. We have the handheld, and this is where this is the high-end terrestrial, which is sitting up on a tripod. And we have a backpack, a mobile backpack for indoor, where you just walk around. Even in this room, you just walk all over, and they will capture all the details. So we have UAV, where UAV you can mount where camera, or you can mount a LiDAR system. And of course, we have that most expensive mobile system that you are capturing roads, long cross countries terrain. So
You got the cost of something like that, roughly. Like different things, just around.
okay. The cost of that is more than $1 million. Right? This cost is more than $1 million. This cost is about 150. This is coming down because the market is flooded with a lot of handheld. And probably you can get it about 20,000. Right? This is an expensive one. It's about 150. That is about 200.
So just an appreciation of the cost and
So yeah. So that's why when you want to carry out certain jobs, as an engineer, you also need to put some consideration on the costing. Right? It's not say I need that 3D data. However, you're going to blow up your whole budget. Right? Okay, let me do maybe a quick demo on how you have LiDAR data and how we do some processing work.
so I think this is like a demonstration moment on when you capture a lot of information. What does it take to clean it up? How do you move your collected data from the site back to the computer? How do you process it to the next stage, and how do you make use of it? Oh, okay. Then you can go inside. Oh, hello.
Okay, this is one of the real work project that we are now currently being involved with a contractor, and we are asked to do some 3D mapping so that they can do some studies on how to do their construction work. So if I were to put up all these are the point clouds, LiDAR captured point clouds. You were able to see that there is a complete mesh, I mean a cloud, and to visualize, you're going to have a bit of a problem trying to visualize if everything is in the same color. So I have already do some segmentation, cleaning out of the noise. What we call noise means when you are doing the capturing, you have people walking past, you have car moving here and there. Those are the noise which are unwanted in the capturing of data, right? So we need to clean out all these noises, and before we do some registration, to combine all the setup, all the clouds into as one whole model. Yeah. And of course, when you put it in, everything what we have is only we have intensity, and we have intensities, and we have some others attribute that is tagged to the point. So we need to do some classification. So by doing classification, we has already split up over as building, ground, okay, some fire hydrant here, trees, and lamp posts. So and we have also do some colorization for better visualization, right? So if you look at how you can play and view what has been captured on site before, as an engineers, to prepare what you want to plan and what you're going to do, all right, with the site here. So let me, okay, I off the building. So when I off everything, right, I leave only the ground. So the current ground, you can see, all right, for this ground is, of course, it's not that type of slopey ground. It's only a flat ground, right? And for the engineers, they will not look at it. Okay, since this is a flat ground, so I have some staircase, some railing here and there, but I want to know what other features that is there here. So you can have lamp post, you can off it, on it, and then you can even on the utilities, which is the fire hydrant, and of course the trees. So with all this data set, right, it's much easier for an engineers or QP to plan what they're going to put, where they are going to put their design. For instance, all right, I have this design structure, right? So this design structure will comes from your guys as an engineers or architects, that you say, look, I want to put something here. So what are the things that is obstructing me, right? So we know that, oh, you have some lampposts that you need to remove. You got an electrical box here that you need to remove. And probably you do have some trees that you need to chop. So these are the decision making where if you have sort of clouds over.
So I think how an engineering company uses some of these survey information is that once the surveyor goes down on site and gives us sufficient enough resolution to work with, and then that's when we start to do our feasibility study. Say we need to construct a structure here, what are the things that we need to move out of the way? What are the costs of some of these diversion of the services and diversion of the lampposts? And actually, after we take it out, do we have to reinstate it back after we're done? So I think most of the time, a lot of the decision making is actually brought back to the office to be discussed and mapped out. So I think we use this very often to get like a client's approval before we go to the next stage of design. And having information like that actually helps to move the project forward very quickly. Yeah.
So coming back, we look at how this integration of data, how does it works, right? So we start out with data capturing on site using the various technology, and with all this capturing of data set, we will come back. We do a post processing and registration, and also do the georeferencing to the local grids. And from there, we will do some generations of themes, DTM or surface features. So as what that's now I've put up that demo, so you can ever see that that particular clouds has already been geo-referenced. Actually, is on the actual site condition now. All right. So this is how we do the workflow where we generate all this information, and the last part is where the engineers and QP come in to do their design, do their modeling, all right, using this data set. And of course, surveyors also will use that to do their calculation. So it's the same processing that in the earlier slides we have. And so we will let's take a look at the step by step of how we get this process going. So the first step is, of course, after when you capture with all the instrument, you have to import the formats into the software, right? Creating these project folders, right? And of course, you also need to do the coordinate system referencing to make sure that it goes back into your actual local grid. Right. Okay. So we have this registration. Because every cloud that you scan, every point, every station that you scan, actually they are not related to each other. What I mean by not related means you will not have a continuously seamless matching of points, right? For instance, if you look at this, if this is a table of one whole length of table, but if you were to scan at this position, and then when you move to the next position, where you capture the same table, these two tables, they won't be in the same alignment because the way we set up the equipment is not on the same alignment or same plane, right? So, and of course, we will do the cleaning, as I say, the cleaning of the noise, the filtering of all those unwanted data set, and we do the classification of the data set to separate it out so that you can easily know what this data set represents. So after when all the cloud that has been cleaned, we will import it into the software, all right, to generate surfaces. So you will know that what terrain or how the terrain looks like, and whether there are gaps that you have missed out or not, that you need to go back and cover all these gaps to have a better or a complete site condition. And with the generation of teams and DTM, you're able to export it out into CADs, where designers will able to do their designing, do their analysis studies, and put in whatever structure that they want to put in. So I show you another demo, a little quick one on what do I mean by not misalignment. Okay, when you capture the 3D data set, so we are talking in terms of millions of points. At if by looking at here, these are millions of points in this one setup. So and of course these are noise. If you look at this, these are what we call noise, where the vehicles have just passed by while we are doing the capturing, and this information not irrelevant to designers. So we need to clean up all this. If not, we might accidentally click onto this information to get the XYZ.
Hey, Mr.
Right.
I checked something. So let's say there's a white color spot behind the car. Is that captured in the 3D scan as well?
White color spot in the car. What do you mean?
This part.
Oh no. Okay, this anything that is behind an object will not be captured, right? So that's why you will see that these are shadow, right? These are shadow. So if you have a shadow, I mean, however, because this is a moving vehicle, so moving vehicle, the next setup that you go, you will capture, you will cover this shadow spots, right? So you see, if now what I have is the first setup. So we're going to put the second setup that we comes in is
now it's nice already. Now it's
all right. It's like this one. So it's like this direction where the vehicle has already left. So when we are over here, we will capture the shadow, right? So it's what could I naturally covered, right? Unless that object is stationary and then it doesn't move. So if it doesn't move, we will have an issue, right? So probably we need to come back another day, right? Okay. So doing two setup without any registration yet. If you look at here, we have two lampposts, right? Which what I mean is, if you have not even aligned, do any alignment of this, you have a mismatch. So a mismatch will be a misinformation to the designer. So you you need to do this registration. I mean, every setup, you will definitely you have to do an registration to bring both of them back in. So okay, let me do a quick registration of this point. We use the algorithm of the ICP, which what it means is the closest point between point to point, right? So the algorithms they will recognize certain points to push the whole registration back. So if you look at the lamppost now, it's a single lamppost now. Right. So this is that means this stitching between setup 1 and setup 2, they have bring it all in line. So if you goes on, let's say you have a 50 over setup, then probably you need to run a cycle of it to get everything back as a single model with no misalignment, right? And
I think.
yeah.
So actually, you can imagine that this is just a simple two scan process, one on the left side on the road, and then repeated again maybe like five or 10 meters away on the opposite side of the road. And if let's say you continue to do 3D scans for the say the HDB estates, you could be looking at like a good 50 scans or 60 scans, considering you have some blind spots, you have some corners that you're unable to scan. And later when you bring all this information back into the office for post-processing, now I think it's like pretty fast. You get like the scan in a minute. And then sometimes when you start to layer on layer and start to press the button, I think it could end up running for a long time. So I think some of these advantages of, like, let's say you're a little bit kiasu and you thought, hey, why don't I just do another 3 or 4 more scans in this corner? I go to the other corner, yeah, I just do another 3 or 4 more scans just in case. And then when you go back, actually there's a lot of information to deal with. So I think overall for surveying work in the field, a lot of it is on experience. You try to do it skillfully, with sufficient number of scans, but not too much that when you go back, you got another big headache to deal with later on.
Yeah. That's why we try not to oversample. We call it oversample, right? Oversampling will be a big problem in the processing unless you have a very good PC or some server that is running super fast, right? If not, things like, okay, for instance, this project that I've been on, it took 24 hours, right, to stitch everything up to become one model itself. So try not to oversample, right? And also not to undersample. So undersample is also a problem because some of the detail might be missing, and you have to go back. So by going back, that a cost and time. In Singapore, of course, it's easy to move around, but places even like if you work in Malaysia, right? Malaysia, there's a big problem if you do undersampling because the traveling is very far. And some of the places that you go in, very rural, access problem, and you might need to go in with helicopter just to drop the whole survey team there and let them do the work, pick them up the next day. So all these costs. So planning and capturing 3D data is not just press of a button and say yes, I can get everything done, right? But then you also need a proper planning. You still need to do some decision making to make sure that everything runs smoothly. So there is some good practice and some pitfall that while carrying out 3D data capturing. You need to have a consistent coordinate system, right? So you cannot have 2 different types of coordinate system, and then you will have a sort of mismatch of data capturing. And of course, you need regular backups. You are capturing gigabytes, probably 100, 200 gigabytes at one go. If you just put it into one computer without any backups, then anything goes wrong, it's just too bad. All right. So those misalignment scan, you also will need to take care of, not by just looking at the point clouds, but sometimes very minute this misalignment do happens, right? And which you are unable to see, right? So as I said, also we try not to over smooth the surface because as engineers, the terrains are the most critical part in your design, right? To smooth it too much, then it will not deplete the actual condition of the site. So let us summarize from the capturing of raw data to engineering service. We captured using sensors, then we do the post-processing, and we move into CAD to do the topography or do the modeling. So we were able to have some clean and accurate 3D service, which will enable the engineers to do their design work. Okay, we look at some of the application in engineering. Right? Why does it matters? Right? That we need 3D geospatial information. Okay. 3D mapping is not just some 3D point clouds, some animation that you know, the games that they are playing, right? So because for engineers, it's to turn whatever been captured into design intelligence, right? Improving the precision, and then you reduce your rework, and of course, enhancing the safety. So in this section, we will try to see again UAV, LiDAR, and 3D modeling workflow that powers the civil engineering application. So we have generally engineers probably are involved in highway, road design, infrastructures, right? And with UAV, mobile laser scanning, this will be a benefit to engineers where you have a rapid topo survey. You can have accurate DTM for your corridor design. And then, of course, you can even visualize the existing route where you can do your interchange connection, right? Or so forth.
You're saying this one is the $1 million one, the one that's more on top. Is that that's the one, right? Yeah.
That is the $1 million. But of course, if you were to cut costs, and but however, if you have sometimes you can do using the backpack as a form of exercise, where you walk about 10 kilometers, right? With triple mode, I think we say we look at about 10 kilo, 15 kilo. For the meal, I think no issue. You all been to NS? Of you? Nobody? Still not in the NS? Huh? Are you all in the NS? Have you finished your NS? So I think shouldn't be any problem carrying a backpack of 15 kilo, right? No, huh? Okay, the second application probably bridges and structures. We have in Singapore, we have a lot of bridges. We have a lot of flyovers, underground tunnels, all this to survey. So things like pre and post, right? Before you construct, you do a survey. Then after you construct, you also do a survey to document what has been built. And of course, bridges will be useful if you have 3D information where engineers can determine what are the clearances so that movement of high vehicles will not crash into these structures. All right. So you also can use it for deformation settlement, right? Deformation and settlements are some of the works. I think if you happen to walk around any MRT work site, you will see a lot of all these sensor markers that has been laid on the ground and the structures. So all this will be a very good information for engineers. And we have that one as my earlier video that showed the UAV that flies up to take some construction site. This is meant for construction progress report and quality controls. And of course, sometimes you use it as a safety feature to study what are the safety condition of the current site is. And the fourth application we have done a lot of earthwork volume calculation. So now what I can say is Changi Airport Terminal 5, right? Before the construction of this terminal, which is currently is already halfway through, I think, for the runway, they do stock up a lot of stockpile, right? Because in the airport, I think for safety purpose, we are not allowed to put in those concrete blocks which you see in some of the construction site outside that weigh tons and measure 2 meter by 2 meter. We stack it up as high as possible to test, to give a load test on the existing ground. So in the airport itself, we are not allowed to put this type of hard structure, which is due to safety of the aircraft. So what they do is they stack up sand, right? So they stack up sand. So when you stack up sand, this type of application where you come in with some LiDAR scanning, you're able to capture this sand and you do a calculation of the whole volume and you're able to convert the density of the sand and you will know what is the weight of the sand. And with the weight over the period of time on the ground, what it affects how much the settlement of this ground, right? So these are the data that you can capture, and you can also use it for analysis to studies until that you make sure that there's no more settlement before you start your construction work of your infrastructure. The other one, okay, I think this is a fifth application.
We show the city.
Right. This is the model of the 3D city model, which is presented, I think, generated by SLA. And to come up with all these structures and the landscape, SLA have conducted an area survey, right? Flying the whole nation over the whole of Singapore, capturing all the area photography. And they have that mobile scanner that move on the ground to capture what is on the ground where aerial photography has been obstructed. With both systems, they combine the photography and the LiDAR information, and they come out with this 3D city model, which will help the planner, right, to decide how well or what future plans that they're going to build for Singapore. For instance, if you look at this is the Marina Bay side, right? So probably like you already planned there. They're going to come out another new casino over here, right? And further down, they have some planning, which is the founders memorial. So this is where the 3D mappings comes in.
So I think on a very big scale,
on a city planning level, actually you can see applications of LiDAR and mobile scanning, mobile LiDAR, and even something like an image to produce an image like that. You can imagine the amount of work that goes in and the level of accuracy that was done, and the difficulty in trying to stitch different models of different LiDAR scans together to come up with this final image where people can start to plan, for example, the next casino or the next founders memorial, so on and so forth. So these are actually the real applications that we use, and we can see that even the government is stepping ahead in this, adopting some of these technologies, especially with regards to planning Singapore.
Okay, the next applications is for deformations and monitoring studies. So you can also use 3D mapping to periodically scan certain structures that you are looking for deformation, or you are looking for embankment slope failures, or this, right? So this scanner were able to detect millimeters movement over a period of time, and you use a certain sort of algorithm that able to calculate different periods of data set to tell you whether is there any deformation, any movement of the structure. It's a bit slightly a bit difficult here.
So I think for engineers, a lot of times deformation study, what do you do with monitoring data? Most of our decisions actually come from the survey data that we receive, and then from there we try to do some kind of engineering judgment to make the next step, whether to stabilize the slope, or actually we can just leave it and wait for further movement first. So some tools like that really help, because in the past, when if you're only going to use a total station to survey the slope, your information is just like what Mr. Heng went through, just a point or very sparse information. But now you can actually detect not so obvious movements that you cannot detect with your eyes, and use technology to enhance it and to even like calculate it.
Okay, this is just for studies, right? It's not a project. We just need to understand whether in this algorithm, how does it tell us that there is changes to this stockpile over here, right? So we have an initial stockpile that is in this shape. So over the period, because there are movements, the stockpiles have been moved out of sight, right? But then we need to know how much is been moved off, right? Then when we come in a quarterly time, which is 3 months time, we found that the shape has changed, right? So physically, of course, I'm showing you this now is because I'm just trying to show you what is the difference. But in terms of if you do monitoring, of course, you will not see the whole thing from a big shape to a small shape, because the movement probably is in millimeter. So this is just a sort of a presentation to show you.
Actually, you can see that being a surveyor with working with 3D scans, you actually rely on a lot of computational softwares to make sense of the data and your cloud point model. So I think it's one thing to measure it's one thing to take into account the cloud points, and it's another thing to actually start to do measurements between them, and then that's when the data sets that you get are really useful. So actually, this is the gray one is.
So using the algorithm, we are able to calculate between the two surfaces, what is the difference, right? So if you look at the scale bar here, we have the blue to the gray. So this, if you on off the actual phase, okay, let's look at the initial. So the initial was almost like an ice box, right? A complete box. Then 3 months later, there's some movement. So it's sloped down. Okay. So 3 months later, some of this portion has already been gone. So if you do using the algorithm of M3C2 algorithm, what they will show you, they will going to tell you that the gray part has already been removed, right? The zero, the green up to the zero figure, anything that is below that is not being moved, but towards the blue, there is some uncertainty. So this is how the algorithm compare between two surfaces and to tell you whether is there a movement or is there no movement, right? So even the calculation also will put some gray area telling you there is some uncertainty that probably due to some noise that is not being cleaned off, right? Which is not the actual material that we have captured. Probably somebody that walked past or some machine that move over while we are capturing. So this is how, as a surveyor, we were able to put up some report and let whoever the authority or the engineers know that, okay, that there is some movement here and there's some movement over there in this manner. Now,
Go straight to digital twin.
okay, we have been talking about the technology using the primitive way, then we move on 2D to 3D. So we come back now to digital twins. Okay, what is digital twins, right? So everybody will be asking this. If you initially when this term comes to me, I also was wondering, are we comparing photos and against the data that we are capturing? And I was wrong. Okay, I was wrong. Right, digital twins means it's a virtual representations of your object. Okay, there's a system, a process that you put on some sensor, and this will be continuously updated with real-time data, and it feedback from the real world, all right, from the real world counterpart to all this sensor, and you will feedback into your this 3D data that you have captured, right? So what you have here now is that you will able to distinguish if you put up this not this.
Right.
I can go back. Yes.
This one. I think you can go to the trend. No, I can go back to.
So for digital twin, I think it's on integrating sensors to the 3D models that you saw just now and making sense of the sensor data to show the changes real time on site.
Okay, maybe I just explain on it. You just okay, we just visualize a bridge. So right, first we capture this 3D data model, and then we model this bridge. Right. With this bridge, we already have the XYZ information of the bridge. Then the next part is that physically we will go out with sensors. So with sensors, that means we will attach all these sensors probably underneath the bridge or on the pillar of the bridge. Right. So this sensor will capture, for instance, if there is human movement, we have a lot of human movement on this bridge. And this is probably is a suspend bridge, right? So there is a sort of vibration on the bridge. So the bridge will be shaking. So this sensor will pick up all this data of the movement. That means the shaking movement of the bridge, right? And how it sway, right? How it sway and how it move up and down. So all these are captured with this electronic sensor, and it will be feedback, right, to Internet of Things, all right, IoT or cameras, everything, and you feedback right to the server. So together, combining with the 3D geospatial data, you were able to detect, all right, or do a study. The engineers were able to do these studies whether if the movement of this bridge carry on at this amount of shaking, will it be safe? Right? Will it be safe? So this is the question of the engineer. So as an engineer, you ask all this. So if you think that, oh no, it has already overshot your safety factors, right, a certain amount, then something must be done. So it's a preempt. So before an accident happens, so you have already preempt to rectify, all right, this bridge. So to install more support or whatever things you deem that is necessary for the safety of the public that cross this bridge. So this is what we meant by a digital twin, right? Okay. Okay, we before we wrap up, let's look at the future. So we have gone from mapping to modeling, and then to some intelligent system. So this data are continuously flowing, right? So in real time, since if you are moving towards a digital twin, and as a engineer, right, you need to understand the workflow, and of course, how to interpolate all the data, all the information that has been given to you, and you do an automation, do some analytical studies, and this is the evolution from where the old days we have a plain table, and we just all the way comes we have digital twins, but we won't know what is coming, right? So even though probably after you graduate, there might be something new here. Right. So technology is moving at a very fast rate. So just be prepared. Okay, coming for the first thing we are looking in now at this moment, everybody is talking about AI, right? So AI has changed a lot of engineering aspects, right? So we also now using AI to do some of our work, to do extraction, because we are dealing with millions or trillions of data. So to use manual intervention, no, you will never get the job done. So AI, I think, will be part of our life. Right? So, and of course, the digital twins will be there, and I think this one will probably go for many years. Right? Yes. And of course, dealing with tons of data, we no more small hard disks that we can use anymore. So we are looking at cloud sharing, and where all your processing will be cloud-based, and of course, interaction will also be on cloud. And of course, gamers probably have already been to this AR and VR. A lot of gamers here, I look at it, right? So for the 3D data capturing, probably we will also need to get into this AR and VR, where I mean, you already have so much of information. Why don't we just mix AR and VR into it, and probably you can have a sort of virtual views of what is on ground. And this IoT and real-time sensoring will be there. So this is part of how the capturing of these sensors things work. Okay, so what is the future role for engineers, surveyors? Engineers, surveyors, we probably are decision makers, right? But we also need to discipline ourselves, right? To have some ethics in the data interpretation, right? So it doesn't mean that we have beautiful visualized point clouds or whatever information coming in from IoT, right? We neglect our ethics. So just keep to that. So let us just a quick recap. We have touched on the fundamental, how the acquires data, and processing, modeling, and the application, and of course the future that we'll see what is coming. Right? Okay, final thought. Just stay curious, all right, for you guys, all right? Stay curious and be adaptable. So change to the new environment. Of course, don't keep on sticking to the old-fashioned way. Right? There are more things that will be involved, right? So it will be a very bright future for you guys, all right? We are ready. For me, I'm over the hill already. Right. So you all will be the those guys that are taking over the baton and make Singapore a good place. Okay. So let me thanks